We were discussing about binomial theorem in the previous lecture. We discussed about the Pascal's triangle. Then we discussed how to expand any given algebraic expression. Here's a quick review. So what would you give an algebraic expression? X plus a raised to the power n. Then the binomial theorem states that this can be expanded as summation r goes from 0 to n NCR x raised to the power n minus r times a raised to the power r. If we open up the summation, so this is how it's going to look like: NC0 x raised to the power n a raised to the power r0 plus NC1 x raised to the power n minus 1 a raised to the power 1 plus NC2 x raised to the power n minus 2 a squared, plus it goes up to the last one, which is NCN x raised to the power n minus n times a raised to the power n. So this is what the expansion of a binomial expression x plus a all raised to the power some positive index n looks like. Now we're going to talk about some important conclusions from this binomial theorem, some that will help us in solving problems. If you have followed lecture number 1, then you could see that I have already worked on some problems, some practice problems, where I have gone ahead and used some of the results that I'm going to talk about right now, and I've already used it. So I'm just going to give you a small theoretical idea how binomial theorem works. So we're going to talk about some important conclusions. So we're going to discuss about some important conclusions that we can derive from the given binomial theorem. So this is what we're going to talk about now. Okay, let's begin. Okay, so the first thing that we have to understand is that, so let me rewrite it quickly. X plus a raised to the power n equals summation r goes from 0 to n NCR x raised to the power n minus r times a raised to the power r. So the first thing that we are going to see here, that the r, as you have seen, goes from 0 to n. So the first conclusion that we get, the number of terms. It's about the number of terms. So the number of terms and the expansion of x plus a raised to the power n is equals to n plus 1. For example, so if we have x plus a squared, so here n is equals to 2. So the number of terms is equals to n plus 1, and that should give us 3, and that's true. Now without applying binomial expression, you can say that the expansion of x plus a whole squared is x squared plus 2 times the product of x and a plus a squared. So yeah, now you can say there's 3 terms. There's always one more than the index n. So this is true for any expansion. So this is a conclusion number 1 about the number of terms. Next, we go to the second conclusion. The second conclusion states that the sum of the indices, of x and a in each of the terms. In each of the terms is equal to n. What does that mean? Let me reiterate it with the help of an example. So I'm going to take the binomial x plus a and raise it to a positive index 4. So let's quickly apply. So this is 4c0 x raised to the power 4 a raised to the power 0 plus 4c1 x raised to the power 4 minus 1 is 3 and a plus 4c2 x squared a squared plus 4c3 x a cube, and the last term, which is 4c4 x raised to the power 0 times a raised to the power 4. So if we look at the index of x for the first term, so here the index of x is 4 and the index of a is 0. So when we add the indexes, what we get is 4. Now this is equals to n. Now this is true for any of the term. So let me pick up the third term. So in this case, the index of x is 2 and the index of a is 2. So 2 plus 2, 4, which is equivalent to n. So you pick up any terms in the expansion of a given binomial. And what we're going to see is that the sum of the indices of x and a is always going to be equal to n. So this is conclusion number 2. Okay. Now conclusion number 3. The conclusion number 3 is more of a combination problem. To since NCR, so this comes from combination. This is NCR is always equivalent to NC n minus R. So for R equals to 0, 1, 2 up to n. Okay, so if this is true, so for r equals to 0 implies nc0 is equals to ncn. You can check it out. What is nc0? This is n factorial over 0 factorial times n minus 0, which is n factorial. This is n factorial over n factorial, and n minus n is 0 factorial. So we can see this holds true. Then we have r equals to 1. So r equals to 1 will give nc1 must be equals to nc n minus 1. You can also check this out. This will be n factorial over 1 factorial times n minus 1 factorial. Which is equals to n factorial over n minus 1 factorial, and n minus 1 would give us 1 factorial. So this is true. So if this we can continue. So this is for any values of r. So let's say r is equals to 13. Then nc13 must be equals to nc n minus 13. So these values are always equal. So this is our conclusion number 3. Now we go to conclusion number 4. So so we have x plus a. Let me write it again. So I'm writing it over and over again instead of copying. So this we should do it. This is a good practice. This will help you remember the binomial theorem. So x plus a raised to the power of n is the summation r goes from 0 to n. NCR x raised to the power n minus r times a raised to the power r. So here what we're going to do is we're going to replace a by negative of a. So if you do it, then we should get x plus, so negative of a raised to the power n equals to r goes from 0 to n ncr times x raised to the power n minus r times negative a raised to the power of r. So x plus or minus will give us x minus a raised to the power of n. So this is, okay, let me first quickly write it down. NCR. Now this, we can pull out this minus, this negative sign from inside of a, and we can write it as negative 1 raised to the power of r. So x raised to the power n minus r times a raised to the power r. So this is the binomial expansion of x minus a raised to the power some positive integer n. So we can work with x plus a, x minus a. We have already worked out on some problems in lecture number 1. So there's one question that I worked on. So this is twice x minus thrice of y all raised to the power 9. I'm not going to solve it. You can, if you want to find out the solution, you can go to lecture number 1. So here I'm only going to rewrite it in the notation form. So this would be sigma r equals to 0 m n c r goes from 0 to n. So no, it's not n. So this will be 9c r 9cr negative 1 raised to the power of r times x raised to the power 9 minus r times a raised to the power r. Now we are going to replace x and a by this value. So this is r equals to 0 to n c r negative 1 raised to the power of r times, so what is x here? So x is actually 2x raised to the power 9 minus r times a. A is now only thrice of y because we have already taken care of the minus sign here, which is minus 1 raised to the power of r. So it is positive thrice of y all raised to the power of r. So we can expand the summation, and then we get the final value. So this is conclusion number 4. Now conclusion number 5. Again I'm rewriting it. X plus a raised to the power n equals sigma r goes from 0 to n ncr x raised to the power of n minus r times a raised to the power of r. So now what we're going to do is we're going to substitute x. We're going to substitute x with 1 and a with x. This is simply a substitution. Then this would look like 1 plus x. X and plus x the sign. So 1 plus x all raised to the power n comes r equals to 0 to n ncr 1 raised to the power of n minus r times x raised to the power r, which is equivalent to saying summation r going from 0 to n ncr. Now this is going to be 1. 1 raised to the power, any index is always 1. So this is 1. So we will left with only x raised to the power of r. That's it. So this is the expansion of 1 plus x whole raised to the power of n. Okay. So this is my conclusion. Now conclusion number 6 is quite similar to conclusion number 5. All we're going to do is juggle the values in such a way that now we're considering x is equals to a and a is equals to 1. So that should give us, so it was x plus a, so now we'll have okay, wait, my bad. So what we're going to do, let's keep x as x only. Let's keep x as x. What we're going to do is only replace a with 1. So this is x plus 1 raised to the power of n. So this is sigma r goes to 0 to n ncr x raised to the power n minus r times 1 raised to the power of r, which is equals to sigma r equals to 0 to n ncr x raised to the power n minus r. So what's the now what is the difference between 5 and 6? So in 5 what we're doing, so here when we expand this expression, then what we're going to get, so the powers of x are going to be the ascending powers. So here we get ascending powers of x. Then here in the second case we're going to get the descending powers of x. So that's the thing. So we're going to talk more about this when we are working on some numericals, then this will become much more clear. Okay, so now I'm simply going to write 7. I'm not going to go into the details of writing it. Now what we're going to do now, we're going to replace x with 1 and a with negative x. So we should get 1 minus x all raised to the power of n. So this is summation, r goes from 0 to n, ncr. I'm straight away writing the result. So this is negative 1 raised to the power of r and x raised to the power of r. So this is what we should get. So this is number 7, and then we go to number 8. Conclusion number 8. Conclusion number 8 says that the coefficient of the r plus 1th term in the expression, this is a very important one, the coefficient of the r plus 1th term in the expansion 1 plus x raised to the power of n is ncr. That's it. So that's it for, let's do a quick example. So that would mean that if I have an expression 1 plus x raised to the power of 7, then we can say what is r equals. So let r be equals to 3, then r plus 1 is 4. Okay, so t4 is simply 7cr, just 7c3. You can find out the value of 7c3. So this is the value of the coefficient. Okay, yeah, that's it. This much conclusion. So there's one more conclusion. Okay, it's much better to, instead of stating that as a conclusion, so I'm simply going to write it down. You can work it out. We're going to do some problems based on that. So conclusion number 10. Okay, conclusion number 10. Is it 10? Well, oh, this should be 9. Then this should be 9, not 10. Conclusion number 9. Okay, so x plus a raised to the power n plus x minus a raised to the power of n. So if we expand this, then we should get 2 times nc0 x raised to the power of n and a raised to the power of 0. Then plus nc2, not nc1, nc2, so x raised to the power n minus 2 a squared, and so forth, and so forth. Okay, I can check this out. You can try this out. You can expand x plus a raised to the power n and x minus a to the power n separately and add them, and you should get this particular result. Second one is x plus a to the power of n minus x minus a raised to the power of n. This is equals to 2 times. Now in the previous case it started from nc0, now it's going to start from nc1. So x raised to the power of n minus 1, a raised to the power of 1 plus nc3, x raised to the power of n minus 3 times a cube, and dot dot dot. So it's going to go on. So these are some 9 conclusions that we can draw from our binomial theorem. So I wish you don't have to worry about memorizing any of them. It's pretty much basic. And as we do more numericals, then those things will get clearer. Okay, so we're going to work on some problems. I'm going to continue where we left off with lecture number 1. We're going to solve some more problems, and that should help us understand binomial theorem. Okay, see you in the next class. Bye.